This video is on Chapter 16, Section F, the roots of complex numbers. And this will be the final video for Chapter 16. Section G, if you look at it, it just really has a few problems in it, which are interesting problems, really good applications of complex numbers to other topics that we've seen throughout the course, but nothing that I need to do a video on its own. Now, Section E, de Moivre's theorem, that was about taking a complex number and raising it to a power. And Section F is kind of related to that. We're going to be taking roots of complex numbers now. So for starters, some notes. We're going to be solving this equation right here. Z to the power of n is equal to c, where c could be any complex number. Z will also be a complex number. We start from using a principle that we learned back in Chapter 6, which said that if we had a real polynomial of degree n, a real polynomial equation, I should say, then there would be n solutions to that polynomial equation. Some of the solutions would be complex numbers themselves, and we're just going to apply that here. So if I have z to the power of n equals c, how many solutions are there to that equation? Well, there are going to be n of them. There are exactly n nth roots of the number c. Next, if c happens to be a real number, then the complex roots would occur in conjugate pairs. That's what we saw back in Chapter 6. Chapter 6, we were solving for, like x to the power of n equals some number or whatever, but it was a real number, so we saw that all the complex roots occurred in conjugate pairs. That is not true if c is not a real number. So if c happens to be complex, then its complex roots will not occur in conjugate pairs. And I think we'll see why with some, there's a geometrical argument that we'll look at in a minute that I think will make that obvious. All of these roots of z to the n, all of these complex numbers, they're all going to have the same modulus. And that modulus will just be the modulus of our original number c to the power of 1 over n. I think that makes sense, right? We're taking the nth root of c. All right. For the geometry, I just referenced geometry a moment ago. On an Argand diagram, all of the roots will be on a circle with the radius of modulus c to the power of 1 over n. And there's not only that, will they be on the circle, but they're all going to be equally spaced around the circle. And by drawing them as vectors tip to tail, we're going to get a regular polygon. What this means is that as we go through these problems, there will be a geometrical argument that we could make to solve them, and there will also be an algebraic argument to be made. I have never seen a mark scheme, at least that I can recall, that specifically referred to the geometrical argument. They all seem to talk about the algebraic method. So I will be modeling that in every single question, and I am requesting that you do the same. I can't guarantee that you would get full marks on an IB exam if you use just the geometry. Anyway, let's look at some examples. Here's just a common term. We're going to see this in a lot of problems. Roots of unity. Unity is just a fancy word for saying 1. Okay, so the nth roots of unity are just the nth roots of 1. Let's talk about the fourth roots of 1. This is one that we can do without thinking too much about complex numbers. So what numbers raised to the fourth power should give us 1? Well, obviously 1. 1 to the fourth is 1. Negative 1 also. I can come up with those two off the top of my head. And the other two aren't too tough to think about. Let's do this by factoring, first of all. So we can move the 1 over. We got z to the fourth minus 1. That's a difference of 2 squares. So we can factor that out. And then I realized that the second factor pair here is also a difference of 2 squares. So we can break that one up. And even the first one, z squared plus 1, that can be factored into a difference of, well, a sum of 2 squares with complex numbers. If you weren't immediately thinking that, then okay, you're just going to solve z squared is equal to negative 1, and clearly you're going to get I plus or minus I from that. So here we have the fourth roots of 1 are plus and minus 1 and plus or minus I. Now that's great, but unfortunately we're not always going to have something that we can factor so easily, so we're going to focus on this thing called the nth roots method. It's going to look like this. So we have z to the power of 4 is equal to 1. And here I've just got 1 on an Argand diagram. 1 as a complex number, well, yeah, okay, it's 1, but that's also 1 times cis of 0. But it doesn't have to be only 0, because we could add 2 pi and we'd still end up in the same place, or we could add 4 pi, or, you know, really any integer multiple of 2 pi. Now I want to know what z is, so we're going to take the fourth root of both sides, and then we're going to use de Moivre's theorem. So that gives me z is equal to cis of k 2 pi over 4, or k pi over 2. And then to find the various solutions, we're just going to choose values of k. I will also always do what it says right here. I'm going to start off with k equals 0, and then I'm just going to count up from there. So k equals 0, k equals 1, k equals 2, k equals 3, and so on. I count up to the number of roots that I'm looking for minus 1, so always up to n minus 1. So in this case, 4 minus 1 is 3. So I'm going to use 0, 1, 2, 3. However, you can use any 4 consecutive integers. You'll get the same 4 answers. When when k is equal to 0, then cis of k pi over 2 is equal to cis 0. There we go. When k is equal to 1, then I have cis of pi over 2. When k is equal to 2, we've got cis of pi. And finally, when k is equal to 3, we've got that. So we have 4 answers here. What are those 4 answers? Again, cis of 0 is just 1. Cis of pi over 2, we know that's I. Cis of pi is negative 1. The last one is that. And as far as the geometry of it is concerned, we knew that there would be 4 answers, because it was z to the 4 equals 1. I know that the first one has to be 1. So on my Argand diagram, that would be this green one. Since I know that the other 3 roots all have to be evenly spaced out, well, then I know what the angle of rotation should be in between the 4 of them. The angle of rotation should just be pi over 2. So I could then easily figure out, in this case, what my other 3 roots would be. I might call this one here z1, z2, z3, and z4. Anyway, like I can cheat this. If I know if I know z1 is 1, then I'm just rotating that pi over 2 to figure out z2. I'm rotating that, and I'm rotating that. And there I have the 4 solutions. 1, I, negative 1, negative I. This is a good method to check. This is not the method that I want to encourage us to use because I don't know if it's rigorous enough for the exams. Now, if we were to just imagine for a moment that the initial number was not 1, but was whatever complex number might be represented by that point on the Argand diagram, some arbitrary point in the first quadrant. It really doesn't matter. You can see here that the 4 solutions, in this case, the 4 solutions would all be complex numbers because they still need to be all evenly spaced around, and none of them now are landing on the real axis. But they're not necessarily going to be conjugates, right? I mean, only if this angle happens to be pi over 4, then I would have complex conjugates. But otherwise, I would not have any complex conjugates in this image. So that's speaking back to the point we saw earlier where the complex roots do not necessarily have to come in conjugate pairs. They will not come in conjugate pairs when we're taking the nth root of a complex number, which is exactly what we're going to do here. So let's find the 3 cubed roots of 2 plus 2i. So first thing we're going to do, take we'll figure out what 2 plus 2i is in polar form. So we can draw it out. We've got an image over here. I know it's got a modulus of 2 root 2. The angle is going to be pi over 4, but it could be pi over 4 plus any integer multiple of 2 pi. Now we're going to take the cubed root of both sides. So z is equal to this whole mess on the right, cubed root. Using de Moivre's theorem, the modulus will become 2 root 2 to the power of 1/3. And then we'll have cis of, we multiply through by 1/3 now. We have pi over 12 plus 2k pi over 3. I like to have the same denominator, so I agree with what they're doing here. As far as that the modulus is concerned, keep in mind that 2 root 2 is the same thing as square root of 2 cubed. So that cubed and that 1/3 power are just going to cancel each other out. So we've got square root of 2 out there. And then they're jumping right to the answer. If it was me, I'd be writing this as cis of k8 plus 1 pi over 12. I don't know why I wrote k8 because that's how they wrote it. That looks ridiculous to me. 8k plus 1 pi. And then we're going to set k equal to 0, k equal to 1, and k equal to 2. So now if we let k equal to 0, we're going to have just root 2 cis of pi over 12. That's here. If I let k equal 1, then we're going to have 9 pi over 12, which is the same as 3 pi over 4. So this is actually k equal 1. I would do k equals 2. And if we have k equals 2, then we're going to have root 2 cis of 17 pi over 12. But that's the exact same thing as this one over here. Technically, they did k equals -1. It doesn't matter. Those two are coterminal. So write down either one. This problem did not specify that the angle of rotation needed to be in between anything. So as long as you have three correct answers out of the infinite choices we could have made, you're good to go. I just found out if I click this thing, it changes color. This is amazing. Anyway, this problem looks really terrible. Look at that expression. It's not that bad. We're just going to use polar form and de Moivre's theorem. It's totally fine. Let's check it out. So here's our original problem. Well, can I rewrite anything? Yeah, that numerator, that's just cis of -pi over 6. Look at what the real and imaginary parts are. Recognize that those are sine and cosine values of the same angle. Down below, nothing yet. But we can use de Moivre theorem on everything, right? So this 2, we're going to multiply that through, so that'll be -pi over 3. This is a cis. This is a cis. So we're going to multiply, in our next step, we're going to multiply each of those arguments by 5. We're then going to just start multiplying things together. So if we multiply these two, we're going to add the arguments together. So adding -pi over 2 and 5 pi over 6. And now since we're dividing, we're going to subtract the arguments from each other. And we're here. So what's the modulus? What's the number out in front of the cis? 1. So the modulus is 1. And the argument is just that angle there, -2 pi over 3. That's, if you just look at this for a second, it looks bad. But if you actually think about what's going on, this is actually really easy work. Going to part B. So hence, show that this crazy number here, this is a cubed root of 1. Wow. Well, using it in the easier form that we just worked out, yeah, I mean, if we cube that thing, again, using de Moivre's theorem, the 3 comes in. That just gives me cis of -2 pi. And yes, cis of -2 pi is equal to +1. So that's one of the cube roots of 1. But what are the other 2 cube roots of 1? Well, obviously, 1 is one of them. We have cis of -2 pi over 3 is the second one. And the third one, since 1 is a real number, that means it's just going to be the conjugate pair of this one. So that's going to be cis of 2 pi over 3. Think about that on a circle. We have 1. They need to be evenly spaced. So we're going to have 1 out here. That'll be, angle of rotation there will be 2 pi over 3. -2 pi over 3 is going to be that one. Or +4 pi over 3 if you prefer. It's the same number. Do those 3 vectors make a triangle? If I draw them out tip to tail, an equilateral triangle? Yes. Anyway, moving on to part C now. So 1 minus 2 times this thing times 2 times this thing squared minus 1 is going to be a real number. All right, so we can begin by distributing. And then what do we see here? Well, notice that z cubed right there. We know what z cubed is. We just worked that out in part B. That's going to be 1. That gives me 2 real numbers that we can combine in the middle. And up until this part, I don't really think it's too bad. The next couple of steps, I'm not sure how long I'd have to stare at this before I figured it out on my own. So we know that z cubed is equal to 1, which means if I divide both sides here by z, then I'll get z squared is equal to z to the negative 1. So we're focusing on this z squared here. It's equal to z to the negative 1, but I know what z to the negative 1 is because I know what z is from earlier. So that's z right there. So that's z to the negative 1. Okay. So using de Moivre's theorem, we get cis of 2 pi over 3, just positive. And what's the relationship between that and z? Well, that's the conjugate of it. So that's equal to z star. So this z squared through all of these steps is equal to z star. So my quadratic is now written like this here. And now we have 2z star plus 2z. Wow. What's going to happen there? Well, the imaginary parts from z and from z star, they're going to have opposite signs, but of course the same absolute value, so they're going to cancel out. Z plus z star, in fact, is always a real number no matter what z happens to be. So I have 2 times a real number minus 5. That's certainly a real number as well. Okay, this type of question shows up near the end of paper 1 very, very, very often. In fact, this question is almost identical to one that came out, I think, in 2016 or 17. I don't know. I feel like I've answered this question on multiple IB exams and from multiple textbooks and practice exams I've seen so many times. It's a very popular question type. Please know how to do this. All right, so find the 5th roots of unity, the 5 5th roots of unity, and display them on an Argand diagram. Well, that's not going to be too tough. First, just to throw the 5 roots out, I've got, here's my Argand diagram. I know the first one is going to be here. And then the other 4 need to be evenly spaced around it. So my picture doesn't need to be drawn to scale. It's going to be something like that. I'll label them. There we go. I suppose I should have used W's instead of Z's, but whatever. And what are the angle of rotation? I mean, I guess I'll just say that like each of these angles is congruent. And each one of those angles should be equal to 2 pi divided by 5. From here, we can work out what the 5 5th roots are just from looking at this image. But I'm going to do the work using the methods that we saw earlier as well. So here it is again. Since I know z to the 5th is equal to 1, 1 is the same as cis of 0 plus some integer multiple of 2 pi. Take the 5th root of both sides, use de Moivre's theorem. C is equal to these. We're going to choose values for k. In this case, we'll use 0, 1, 2, 3, and 4. And we get these 5 answers. You can clearly see those from the image. Z2 is here. That's cis of 2 pi over 5. Z3 is here. That's cis of 4 pi over 5. Cis of 6 pi over 5. Cis of 8 pi over 5. So all the answers are clearly, you can get them from that Argand diagram without doing all the algebra. But again, please do all of the algebra. Okay, so letter B. This is cool, and this will work out anytime we're doing a problem with the roots of unity. So if we consider W to be the root with the smallest positive argument, which was cis of 2 pi over 5. Okay, well, we know 1 is one of the roots. We just said w is cis of 2 pi over 5. What is w squared? Well, w squared is going to be cis of 2 pi over 5 squared. And by de Moivre's theorem, that gets us that root right there. So that root is w squared. And then using the same exact reasoning, w cubed is this root, and w to the 4th is this root. So the 5 roots can always be thought of as 1, and then w being the root with the smallest positive argument, w squared, w cubed, blah, 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 blah. What this also means is that w to the 5th is going to be equal to 1. And that's going to be pretty important when I attack letter C. So we're going to simplify this product. Well, come on, that's an easy product, right? When I multiply through here by 1, I'm just going to get 1 plus all those to omega to the 4th. And when I multiply by negative omega, we're going to have minus 1 minus omega minus all the way to minus omega to the 5th. What's going to cancel out here? Well, okay, pretty much everything, except we're going to end up with 1 and then minus omega to the 5th. I think I just slipped into saying omega. I'm sorry. The IB exam, they tend to use this symbol here, which looks like a W, but it's actually the lowercase omega. So if you show me a past paper and you say W out loud, I'll try not to openly mock you, but I will silently be judging you at the very least. It's okay. It's okay. So I'm sorry. I just slipped into saying omega here. Old habits. Anyway, so I've got 1 minus whatever, w to the 5th. What is w to the 5th? W to the 5th is 1. So I have 1 minus w to the 5th. That has to equal 0. Now going back to where where did we get that from? Well, that's equal to this product here. Now I know that 1 minus w, this term, that's not equal to 0. 1 minus w can't be equal to 0 because 1 is not equal to w. Therefore, this sum has to be equal to 0. And that's something we talked about earlier, where the sum of all the roots should equal 0. That has to do with the regular polynomial idea. If I added up these 5 roots, I'd get a regular pentagon. That's a poor picture, but the sum is 0 because we started and ended at the exact same place. And that is your answer for part D. Now, we just solved a problem having to do with the 5th roots of unity. Here, we're going to generalize that to the nth roots of unity. All right, so we had a specific case before. Now we're going to get a little more general. So part A, showing that cis of 2 pi over 5 is the nth root of unity with the smallest positive argument. In the last example, it was cis of 2 pi over 5. Now it's going to be cis of 2 pi over n. Let's see it. So we're solving c to the n equals to 1. We know that 1 is equal to cis of 0 plus some integer multiple of 2 pi. We're going to then take the nth root, both sides. Using de Moivre's theorem, we have cis of k 2 pi over n. The smallest positive argument is going to be when k is equal to 1, right? When we set k equal to 0, then we're just going to have cis of 0, which will be exactly 1. So the smallest positive argument will be when k is 1, which is cis of 2 pi over n. Let's hensify. So our roots, the first one's going to be cis of 0 or 1. That's when k is equal to 0. The next one, w, that's when k is equal to 1. We just found that one. The next one's going to be when k is equal to 2. That's going to give us cis of 4 pi over n, which is the same as w squared. When k is equal to 3, we're going to get cis of 6 pi over n, which is the same as w cubed. When k is 4, we'll get w to the 4th, and so on and so on and so on. We're going to go all the way until k is equal to n minus 1, and that's going to give us w to the n minus 1. Now, showing algebraically that the sum of all n of those roots is equal to 0, we're going to use that same trick that we did in the last one. We're going to take the sum of all of them, and we're going to multiply by w minus 1. All right, so please remember this tactic. Okay, if we want to show that the sum of all the roots is 0, take the sum, multiply by w minus 1 always, and then see what that's equal to. Again, when we multiply through both of these, everything's going to get canceled out except for w to the n minus 1. But we know that w to the n minus 1 is equal to 0. Therefore, one of these two factors has to be equal to 0. We know that it's not w minus 1 because w is not equal to 1. Therefore, it has to be the other factor, which is the sum. All right, so we did a problem where we solved a specific root of unity, and we found out that all the roots summed to 0. Then we generalized to the nth root of unity, and we found that the sum of all the roots equaled 0. We're now going to generalize one more time. We're going to look at the nth roots of any complex number. We're going to call it alpha. We're going to show that the sum of those roots is also equal to 0. It's really going to be done in the exact same way, except this is going to be even more generalized because we don't know what alpha is. We don't know what its modulus is either, so we're going to need to keep all of that in mind. Let's just let alpha be r cis theta. So z to the n is equal to r cis theta plus an integer multiple of 2 pi. Taking nth roots. Now this next step might not be super obvious. What do we have here? This is cis of a sum, theta over n plus 2k pi over n. And we can break that up into a product, cis of theta over n times cis of 2k pi over n. And now we'll just do what we did before, setting k equal to 0, 1, 2, 3, etc., etc., etc. This first one here, this is what we get with k equal to 0, because then this term will just change to 1. Here we've got k equal to 1, k equal to 2, and so on and so on and so on. Why am I breaking them up in this way? Well, like, why didn't I just work directly from here? Well, because we still need to find the sum of all these. And written in this form, this is very nice, because what do all of these individual zeros have in common? They all have an r to the power of 1 over n times cis of theta over n. So we can actually factor that out when we take the sum. So that's that there. And then all the other terms are left inside. And what do we know about those? Those are already the nth roots of unity, and we already worked that out in a previous problem. Therefore, this is all equal to 0. So the entire product is equal to 0. Ta-da! So I don't really have too many like IB exam tips where I can really tell you like, oh, you should really expect this to show up on the exam. They're different every year, and they're very different every year. But a few things that I feel very confident about. Pretty much every single exam has induction. I've made it no secret that I think that induction is something we should all be able to score points on. I try to cover that many, many times throughout the course. Induction is very likely to appear on your exam in May. If you do not see induction on paper 1, then you had better be studying it that night to be ready to see induction on paper 2. Another topic that you should really be on the lookout for has to do with part B, right? So paper 1 and paper 2 are both split up into part A, which is short questions, and part B, which are the long questions. So these tend to be like 10 to 20 marks each. And two things that we see in part B a lot are really long vector questions and also complex number questions. So stuff from this chapter. If you go through paper 1 and you do not see one of these showing up at the end as a really long question, then it will probably be on paper 2 as the really, really long question. So that would give you an idea of the type of things you might want to put some extra emphasis on in between those two tests. For the long vector questions, that's where we're talking about, like, there's multiple lines and planes, and we're finding all sorts of angles of intersection and figuring out what the equations of various things are, and they're just going to ask you to do a million things. For the complex numbers, it's often going to be something about finding the roots of some complex number, maybe drawing them on an Argand diagram, talking about the sum of the roots being equal to 0, and stuff like that. Obviously, there's variations on these themes, and there's certainly plenty of curveballs that they can and have thrown in the past. But at least this gives you a beginning of something that you can expect to be on the test and give you some sense of control over your fate. It's not really any guarantees in life, but hey, it's something. Anyhow, that's the end of chapter 16. As I said, we're not going to do a video on section G because it's just got a couple of mixed review problems. Chapter 16 is awesome. I hope that you enjoyed it too. Complex numbers are just really fascinating stuff. They're very real in the non-mathematical sense of the word. We require them for electrical engineering and currents to work. All sorts of computer animations and stuff is anything done in 2 dimensions is based on them. They can be generalized further to quaternions and octonions and other hyper complex numbers. It gets wild out there, but again, like this all has major uses in various areas of physics. So yes, it is complex, but no, they're not imaginary. They are indeed very real.